Hey everyone, we are going to be talking about polyprotic acids and calculations related to those. And then in the next video, I'll cover the percent ionization comparison that you will find later in this document. All right, so with polyprotic acids, these are a little bit different than when we were working with yesterday, but you're going to see very many similarities between the calculations. So a polyprotic acid is acid with one or more ionizable proton. The general trend that we're going to observe is that each time it undergoes an ionization, we're going to see the Ka get much smaller, meaning a very small amount of hydrogen ions are going to get ionized as it continues to undergo the ionization. And this is related to the increasing difficulty for a hydrogen ion, which is positive, to leave an increasingly charged anion. So as it goes from a neutral to a -1 anion to a -2 anion, it becomes harder and harder for that hydrogen ion to leave, so thus a smaller amount of it is going to actually be able to ionize. One thing that makes these calculations helpful with is that usually when we talk about the hydronium concentration, it's going to just come from the first ionization because the subsequent ionizations are going to be incredibly small. So let's get into some of the calculations so you can see kind of where this is all going to come from. All right, so in absorbic acid, which we're going to use H2 ACS, it's known as vitamin C, but it is a diprotic acid. So two hydrogens, which is what you're going to see here, are going to get ionized. And then we have the Ka1 and the Ka2 for each of those ionizations. So basically wants us to calculate all the concentrations of the ions and then also the pH. So we're going to start with the original weak acid, so H2 ACS, and then this is going to look super similar to yesterday. So it's going to react with water to undergo a reaction where the H2 ACS is going to be your weak acid. It donates a proton. So we have HASC remaining in solution and the hydronium, which you can write hydronium first for whatever reason. I'm writing a second. All right, we're going to set up an ice table. We know we can take water out of that. Okay, we're given the initial concentration of our weak acid as 0.050. There's no initial anion concentration, and hydronium, as we talked about multiple times yesterday, we can start off at 0 because we can ignore the hydronium that's present from the autoionization of water. Based on the balance equation, we know it's going to, and also the fact that it's going to proceed right towards equilibrium. We're going to do -1x for the weak acid and then +1x for each of the products. So we get 0.050 m minus x, x, and x. And then below is where I'm going to kind of start the calculation. I'm going to leave the right-hand side just as some extra information for you to have. Let me slide that up. All right, so our Ka, and we're going to specifically use Ka1 here, is our products over reactants. So we have our anion, which is just the essential conjugate base of our weak acid, times the hydronium ion concentration over the concentration of our weak acid. And we know from yesterday, we can then go ahead and do 1.0 times 10 to the -5th, and that's our Ka given to us up in the problem, is going to be x squared. And then we know that because we have a small Ka, we're going to make the simplifying assumption that we're going to take out that change for the weak acid so that we can simplify them. We'll show at the end again that that's going to be less than 5%. So when you go ahead and you solve for x here, which we know is our concentration of hydronium as well, you should get 7.1 times 10 to the -4. Okay, which then we're going to come back up here and then for this one, when you actually plug in that -x, you will get 0.049. All right, if we do our check quick, which I'm just going to put in green next to this, so if we check for our change in x, I'm just going to put it right off to the side here. That's 7.1 times 10 to the negative 4 over the original weak acid concentration. For this, you end up getting 1.4%, which we know is less than 5%. So it justifies that simplifying assumption that we made. All right, then we can go ahead, and this is where, when we think about our next reaction, so I'm going to leave a little bit of space for myself here. It's going to be where the HASC ion, so this is after the remaining negative ion after the first ionization, that is then going to undergo its own ionization with water. Okay, so one would say that, oh, well, that concentration from the first ionization, we should be combining that with the hydronium from the second. Well, what we find is because the second ionization has a much smaller Ka value, that amount of hydronium really has no significant effect on the pH. So you're always going to, and this is important, note to just summarize for yourself, you're always going to use the concentration of hydronium from the first ionization to calculate your pH value. So we can go ahead here and we're going to do pH is equal to that negative log of hydronium, which is 7.1 times 10 to the negative 4. Okay, and then keeping with the two sig figs, we get 3.15. Okay, so that would be our pH. Now, I do want to show you in this first step how you can understand that. So I'm going to kind of be putting some stuff over to the side that you can choose to write or just listen. So this is because I can use that concentration for hydronium to figure out the pH, because again, that Ka1 is much greater than the Ka2. So the first ionization produces almost all of the hydronium. So if we were to actually do a calculation for it, where we would have our K, I'm not going to actually draw out the ice table. You can look at the copy I attached if you want to. Our Ka2 is 5 times 10 to the negative 2, which would be over x squared over 7.1 times 10 to the negative 4. Okay, that's the concentration of the HAC ion, and then this would be the hydronium. So you can actually look kind of down here. I'm basically setting up that expression, and I'm searching for the two concentrations of hydronium and then the remaining ion. And when you get that, the X, which is the concentration of hydronium from just the second ionization, okay, is equal to 6.0 times 10 to the negative 8. Okay, this is insignificant. If you actually go ahead and you plug in and add this concentration of hydronium to the concentration of hydronium from the first ionization, you'll end up at the exact same, I think it's 3.148. So you get the same pH value. So this is just to show you and help you understand that we can always use this concentration of hydronium from the first ionization. However, we're going to talk about how we need to proceed in order to figure out the other concentrations that it's looking for. All right, so moving on to this piece. Usually when we go to do the second ionization or the third, we don't need to set up a whole ice chart because we're going to simply be using our values from the ice chart above. So for this part here, we're going to be substituting. So we're going to substitute the values from the first ionization into the second to find ASC with a -2 charge. So if we use our equation that we wrote out, which signifies that second ionization, we'll have the Ka2 is equal to that hydronium ion concentration times, that should be -2 there, and that should be -2, sorry, I didn't catch that. So just make sure you fix that on yours, over the HASC ion concentration. So I'm just using that expression to get my Ka set up for the second ionization. Using the information given to us in the original problem, it gave us, I just want to check that I wrote this down right, 5 times 10 to the -12. Okay, in this piece here, we're going to fill in hydronium from the previous piece that we already calculated. So 7.1 times 10 to the -4. Okay, because we're, again, the significant amount of hydronium is from that first ionization that's present in solution. We are then going to be looking for the concentration of the ASC with the -2 charge. And then we also know the concentration of HASC from the previous step, so we can plug that in. So then from there, you're just going to be solving for X, which is your concentration of the remaining ion that we're looking for. And when you solve that, you get 5 times 10 to the -12. So you can see here with the second step, I always have students that say, well, aren't these always going to be the same? At the moment, yes, but keep in mind if we have to do a third ionization, it's a little bit tricky. So I always say make sure you always set this up for yourself so you just get in the habit of understanding where all the values are coming from. So just to summarize the information that we're looking for, it asked us for the concentration of HASC ion, which was the anion after the first ionization that remained. That's going to then get ionized, and that was 7.1 times 10 to the -4. It then asked us for the concentration of the anion after the second ionization, and that's 5 times 10 to the -12. You can see it's much smaller. And then it also just asked us for the pH, which we found above. So pH is equal to 3.15. What I usually see with these questions in AP is in the multiple choice. And really, if you just know that that anion that is at the end of the final ionization, that's always going to be in the lowest concentration. That can save you a whole lot of calculating if you understand the relationship. That's one of the main points I would just make sure really kind of gets through to you as you're going through this. Okay, so I'm just going to kind of walk through another one. It's another diprotic acid. You'll see on a practice coming up a triprotic, so it'll give you a chance to